Welcome back. Today we're starting this new unit on electricity and magnetism. Part of this should be a review of what we learned the first semester when we began with electric charges. From our study of the atom, we know that protons have a positive charge and electrons have a negative charge. And in the atom, the number of protons and electrons are equal in number and they balance out, and the atom is neutral. So before it became an ion, we said that the number of positives in the nucleus was always equal to the number of negative electrons around it. And then in the elemental form, each element was neutral. That means it has a charge of 0. Atoms become charged, and this is another review. They become charged, or ions, by gaining or losing balanced electrons. Now, this is important because electricity is the flow of electrons. So if they're going to flow and they're going to do things, then the electrons have to come from someplace. Okay. Static electricity is the imbalance or accumulation or buildup of electrons on an object. So like when you rub your feet on the floor or something, or maybe you get static cling in stuff in the dryer and it kind of, crinkles as you pull it apart. Okay. All of that is static electricity. So it's electrons that have been transferred from one object to another. The negative and positive charges are static, which means that they're not moving. So we're going to take a look at this little clip on static electricity.
Static electricity. When you rub certain objects or materials together, you can sometimes cause them to be charged with electricity. Rubbing objects together is also known as friction. For example, friction occurs when you rub your feet on a carpet. If you're wearing just your socks, you could get an electric shock when you touch a metal doorknob. That's static electricity. Why does that happen? Here's a simple explanation. You probably already know that all materials are made up of atoms. Atoms are made up of protons and electrons. Protons have a positive charge and are represented by the plus sign. Electrons have a negative charge and are represented by the minus sign. Most materials are neutral, which means they have the same number of protons and electrons. Friction between two objects may cause electrons to move from one material to the other. When the electrons are added to a material, the material has a negative charge. When electrons are taken away from a material, the material has a positive charge. An electrical charge is a force caused by friction. What happens when an object is charged with electricity? Well, materials with the same electric charges repel each other. Here's a demonstration. As this balloon is rubbed with a piece of wool, electrons leave the wool and transfer to the balloon where the electrons will stay. That's why we call it static electricity. They stay put, so the balloon is negatively charged. Now, if we rub wool on another balloon, that balloon too will be negatively charged. If we try to put the two balloons together, they move away or repel. Materials with the same electric charges repel each other. Like charges repel. On the other hand, opposite charges, positive and negative, attract. Here's an example. By rubbing the balloon with wool, the balloon has a negative charge. Next, we're going to positively charge a piece of nylon. To do this, we'll rub the nylon with a plastic bag. Plastic doesn't give up electrons easily. However, it will take on electrons and leave the nylon positively charged. When the positive nylon strip is placed near the negatively charged balloon, they attract each other. Sometimes charges between two objects can become very, very strong, and an electrical spark can jump from the negative charge to the positive charge. This phenomenon happens in nature all the time. We call it lightning. Lightning occurs between two differently charged sections of a cloud, or between a cloud and the Earth.
So what we learned here is that electrons get transferred from one object to another, and then it becomes negatively charged. So over here, the wall or the curtain or whatever this is, it has less electrons than it has protons. So overall, its charge is going to be positive. And the electron buildup is on this balloon, so its overall charge is going to be negative. And this is why if you rub a balloon on like the carpet or something, it's taken next to the curtains, then it'll be attracted. Okay. Now, like all year long, we've had laws of conservation. And all the laws of conservation said whatever it is cannot be created or destroyed, lost or gained, but it can change from one form to another. So here we have the law of conservation of charge. And it says electric charge cannot be created or destroyed, lost or gained, but they can be transferred from one object to another. So like the buildup of that static electricity on the balloon, the charges were transferred from like the carpet or the curtains or your hair. Sometimes you can rub it on there. The electrons were transferred from the one object to the other, but they're not created or destroyed. They're not lost or gained, so they're not disappearing. Okay, and because they can be transferred from one object to another, then opposite charges attract and like charges repel. So just like this is where the electricity and magnetism kind of come into play, like the opposite ends of a magnet attract and the like ends of a magnet repel. An electric field, okay, is this area that's created around the area that has an electric charge, and it'll apply an electric force to an object. Okay. And in that field, just like a magnetic field, an electric force is a push or pull created by the charged objects, and they can act on each other even at a distance due to the electric fields or forces. So as those charges build up, those positive, negatives, it works. You can think of it working like magnetism. You got this electric field caused by the electrons around the object that has the charge with the electrons, like the balloon, and it can act on things even at a distance. So we're going to take a look at this demonstration of this magnetic field around a wire with electricity flowing through it.
I have a piece of plastic through which I've drilled a hole, and then I took a wire and looped it through the hole. I have essentially 10 amps that's flowing in a straight line through the hole in the plastic. I'm now going to sprinkle some iron filings onto the plastic. I will now apply a current, and I will have to tap the plastic to get the iron filings to move. And you can see how the iron filings have rotated to form circles around the wire, indicating the form of the magnetic field intensity generated by a current carrying wire.
And so what he showed us in that video is that as the current passed through the wires, it created this magnetic field, this electric field around the wire. And that's why the iron filings moved in a certain direction. And if you run the current through the wire in the opposite direction, then the magnetic field would change poles. It would be in the opposite direction. So here it shows, if you look at these arrows, it shows it going around this way. And then the other one, it's going around the opposite way. When you change the direction of the current, here it's going from right to left, and here it's going from left to right. And then the field changes. And then as you loop the wire, all these fields add together. And this will be important when we talk about electromagnets, because as they get closer and closer, they start looping together and making big fields. Okay, and then part of this, again, is a review of things that we learned earlier in the year. Okay, when we talked about some of the properties of metals, we said that metals were good conductors of heat and electricity. That meant that they allowed the heat and electricity to flow through them easily. So metals, in particular, are good conductors of heat and electricity. Ionic compounds were good conductors. Remember, they break into ions when dissolved so that they can conduct electricity. An insulator is a material that does not easily allow heat and electricity to flow through them. So things, they like basically the exact opposite of metals: plastic, wood, rubber, covalent compounds. Okay, these things are all insulators. They're not good conductors. And then when we talked about the metalloids, we said the metalloids were semiconductors, and that was one of their important characteristics. So the semiconductor is a material that is in between conduction and of conductors and insulators. And I put in here that these are the metalloids. Okay, so they're the things that computers, chips are made out of, the parts of your cell phone, all those things that carry the information in the circuits. Okay, they allow more control of the flow of electrons under certain conditions, and silicon is a widely used semiconductor. So it's also what's in class. So basically, we take the phone or computer apart. Sometimes the board is green, sometimes it's all brown. That's the silicon. That's the semiconductor. It's the board. Okay. We're going to take a look at this little clip of conductors and insulators.
Conductors and insulators. We've got some different types of materials here that we will try to use in our series circuit used to run a bell. First, let's connect a metal can opener to the circuit. Will it conduct electricity? Yes. Typically, most metals are very good conductors of electricity. So this nail should work well. What about this plastic ruler? Will it conduct electricity? When we turned on the switch, nothing happened. Plastic is not a good conductor. However, it is a great insulator. What about this rubber balloon? What do you think? Rubber is an insulator. Other materials like glass and wood are good insulators as well. You'll notice that most wires coming from electrical equipment are covered with plastic or rubber insulation for safety and protection from electrical shocks. And that's why a utility pole is made of wood. And there are glass insulators on the poles. Insulators permit little or no passage of electricity. There is no perfect electrical conductor. Every type of material puts up resistance to an electric current. Scientists measure resistance in units called ohms. In a circuit, the greater the resistance, the more volts are needed to push the electrons through the circuit. Even the length and thickness of a conductor affect resistance too. For example, thin wire puts up more resistance than a thicker wire, and a longer wire puts up more resistance than a shorter wire, even though they're made of the same material.
All right, there are three ways that heat can transfer. The first one is by direct contact, okay? And this is charging by rubbing or touching. So like if you have a balloon and you rub it on the carpet or your hair or the curtains, then the electrons will transfer from one object to like the curtains or carpet or your hair to the balloon. Now, if electrons leave you or leave the curtains or the carpet and go to the balloon, then the balloon has more negative charges than positives, and whatever it borrowed the electrons from, that has more positives now than negatives. So opposite charges attract. Okay, and this is what also we meant by, the law of conservation of charge. Okay, the charges are not created or destroyed, lost or gained, but they can be transferred from one object to another. So, examples I put in the notes here: static electricity from your feet rubbing on the laundry, when you pull clothes out of the dryer and it sticks together, it makes that kind of sparky sound. When you try and pull it apart, sometimes people get static electricity in their hair and all the hairs want to separate. That's because the hairs all have electrons on them and like charges repel. So the hairs start to repel each other and push apart. Okay. And then induction is the rearrangement of electrons on a neutral object caused by a nearby object. So if the object got extra electrons on it by, induction up here by direct contact, the first one, then it has a magnetic field or an electric field around it now. It has a negative charge. So things that come into that field are going to be affected by the charge that it has. And this is what induction is. It's the rearrangement of electrons on a neutral object caused by a nearby charged objects. Okay? And it works due to those electric field, that charged area around the thing because of the negative or positive charges, depending on whether it gained or lost electrons. Okay, so here's an example of charging by friction or charging by direct contact. Okay, so it shows he rubs this thing on this cloth and now it's picked up electrons. Okay, and so when he moves this blue rod here that has the electron on it, it affects this other object which doesn't have a charge, and the electrons want to transfer from positive to negative. Okay. Whereas the cloth has a bunch of positives on it, so the negatives are going to want to move to it, okay, because opposite charges attract. Okay. Static discharge is a transfer through space, so the object that has a lot of extra built-up electrons on it, eventually there's too many of them and they want to discharge and go so that both of the objects become neutral, the ones with the accumulation of charges and the one that lost the charges. So one of the most common examples is lightning, okay? Or, if you get static electricity on you and you touch a doorknob, you'll see a little spark. That's because in the clouds, like for example, with the lightning, the clouds have a bunch of extra electrons in them. And then all at once they discharge or move to the earth. And that's when we see lightning. Or when you touch the doorknob, the electrons on you transfer to the conductor, which is the metal doorknob. And when they move all at once, that's the discharge. So this one shows a discharge with clouds between the negative base and the positive top area. So the electrons are accumulating here where the clouds are rubbing together, and then the charges want to move. So these negatives move to the earth, which is, the earth, the ground has become positive. So all of a sudden, all at once, all these electrons go shooting down, or sometimes they go in between clouds where you have this positive area of the cloud up here at the top, and this is negative. So the charges move back and forth between the clouds. And that's why sometimes you see the lightning in the sky. Now, a lot of times the lightning will go, when it goes to the ground, it'll go to the nearest tallest object. So in a lot of cases, that's your home. So, I have this cloud, it has these built up electrons in it, and then all of a sudden they're going to discharge and head to the house. Okay. And this is why people put grounding or lightning rods on houses, because if you have a conductor here, the electrons will go to the conductor, and then instead of going into the building, they go into the ground. So it protects the things that you have in the house. So for example, if you have the TV and the washing machine and whatever else plugged in, and all this electricity goes into the building, it'll go into the wires, and then it'll go into the TV or the other electronics, and it can often ruin that stuff. So by capturing it with a conductor, the lightning rod, and sending it into the earth is big enough that it can absorb the electric charges without really changing. So it's a safe place to put the electricity. Also, you see grounding. Most home outlets have 3 holes in them. There's the 2 that go up and down like straight lines, and then there's this third one that sort of looks like a half circle. That third one is the ground. So if something goes wrong with your appliance, it sends the extra electricity back into the ground and back into the earth. So it uses a conductor, as I just said, like this lightning rod, to direct the electric charge into the ground. An electroscope is something that's made of two pieces of foil that can separate, and they can check for charge by induction or direct contact. So here's an example. Like if that kid had rubbed that thing on the balloon and it had absorbed negative charges, the negative charges, the positive charges from these pieces of foil are going to be attracted to these negative charges. And when they do, they're going to move up this way. And that's going to leave extra electrons on the two pieces of foil. And then the extra electrons are going to repel. And same thing here. Positive charges are, the electrons are going to be attracted to these positive charges up here. So they're going to leave the pieces of foil. And then the pieces of foil are going to have positive charges, and they're going to be pushed apart because the like charges repel. So in this case, the electrons move down here and, to a more positive area. So the two pieces of foil have extra electrons on them. Just like static electricity in your hair, they push apart. And if the electrons move up to something that's positively charged and attracted there, when they leave this, these leaves the pieces of foil more positively charged, and they push apart. We're going to take a look at this little video, and he's going to demonstrate an electroscope and explain a little bit more how it works.
Good morning. Right here I have an electroscope. An electroscope is an instrument for demonstrating electric charge. This electroscope has a metal ball on top of a vertical metal rod with a hook on the end of it and two thin foils of aluminum hanging from the hook. That whole apparatus is electrically insulated from its surroundings via the rubber stopper and glass flask. Let's start by charging the electroscope via conduction. First, I will do the entire demonstration, then we will go through it step by step to make sure you understand what is going on. So class, are we ready to demonstrate charging via conduction? Charge this rubber balloon by rubbing it against fur. So now we have a charged rubber balloon. I bring it close to the electroscope, and you can see the foils of the electroscope begin moving apart. And then when I touch the electroscope, I have now charged the electroscope via conduction. So this is a charged electroscope via conduction, and I can touch the electroscope with my finger, pink, and the two foils move back to where they started. That's it, because we're going to go through it step by step. So let's start with the first step. Rubbing the fur on the balloon causes what to happen to the fur and the balloon? Bobby?
Oh, I know that one from before. Electrons move from the fur to the rubber balloon, causing the fur to have an excess positive charge and the rubber balloon to have an excess negative charge. I believe this is called charging by friction.
Correct, although at this point we really are only concerning ourselves with the net negative charge on the rubber balloon. The other object in the demonstration is the electroscope. Bo, before I bring the balloon near the electroscope, what is the approximate net charge of the electroscope?
Well, before you start, the electroscope should have a net charge of 0. It should have a neutral charge, right?
Right. So before we bring the two objects near one another, the electroscope has roughly an equal number of positively charged protons and negatively charged electrons. And the balloon has a larger number of electrons than protons, giving it a net negative charge. Now watch what happens as I bring the rubber balloon near the electroscope. Even before I touch the balloon to the electroscope, the two metal foils at the base of the electroscope are pushed apart from one another. Bobby, why do you think that is?
If the two metal foils are pushed apart from one another, according to the law of charges, they must have the same charge, and there must be an electric force pushing them apart. But I do not know if the net charge on each of the foils is positive or negative.
We can use the law of charges to figure that out as well. We know protons do not easily move because they are in the nucleus of the atoms. That means the electrons are the ones that move, so the electrons in the electroscope, which are negatively charged, are repelled by the negative charges in the balloon and float down to the metal foils. That must mean when the balloon is brought near the electroscope, the metal foils have an excess of electrons or a net negative charge, and an electric force pushes the metal foils away from one another.
That means the top of the electroscope has a net positive charge because there are fewer electrons than protons in the ball at the top of the electroscope, right?
Correct. Now we know what happens before the balloon touches the electroscope. But what happens when the balloon touches the electroscope?
I have no
I do
idea.
not know.
Touching the two objects together allows electrons to transfer between the two objects.
Oh, that means electrons will transfer into the electrically neutral electroscope from the balloon. And that is because the electrons will be attracted to the protons near the top of the electroscope and repelled from one another where they are crowded together, close together in the balloon. Because the rubber balloon transfers some electrons to the electroscope to balance out the net negative charge. Both the rubber balloon and the electroscope end up having some excess electrons.
But the total number of excess electrons in the balloon electroscope system remains the same because the total number of electrons will stay the same.
Conservation of charge. The total electric charge of an isolated system never changes.
Yep.
At this point then, both the balloon and the electroscope have an excess number of electrons causing a net negative charge, which is why the metal foils of the electroscope remain repelled from one another, again, because of the law of charges. Like charges repel. Again, at this point, the electroscope and the balloon both have an excess number of electrons. And then I touch the electroscope, and that causes the foils to no longer be repelled from one another. This is because, compared to the charge on the electroscope, I have a very, very large number of charges, and I act as a ground. An ideal ground is an infinite well of charge carriers, and this is typically the symbol used for a ground. We call it a ground because electrical circuits are literally connected to the earth or the ground. And the earth has, relatively speaking, an infinite number of electrons which we can pull from it or we can give to it. Again, relatively speaking, an infinite number of charges. If something goes wrong in a circuit, the ground will serve as a way to balance out the charges. In this example, when I touch the electroscope is no longer electrically isolated, and the excess electrons on the electroscope flow out of the electroscope into the ground, into me. And the electroscope is now electrically neutral, which is why the foils are no longer repelled from one another. Does that make sense?
Yeah.
Okay, so that is charging by conduction. Two things I want to make sure you realize about charging via conduction. One is that the two objects have to touch, and two is that the two objects end with the same sign of net charge. In this demonstration, both the balloon and the electroscope end with a net negative charge.
You mean before you ground the electroscope, right?
Correct, Bobby, that's before I ground the electroscope.
Okay, we're going to stop here. I want you to answer these questions on your own. And when we come back next time, we'll pick up here. I hope you're having a great day, and we'll see you soon.